Hello, I'm Chris Mack, the professor for this course from Data to Decisions. This is Lecture 3, and in this lecture I'm going to pick a particular example of how data is presented in a typical peer-reviewed journal scientific article. We'll look at it to see if that article presented the data in all of its detail, as we explained in the last lecture, Lecture 2. And the example I picked is chemical vapor deposition. Now, this is not a topic that you need to worry about in terms of the scientific details in this class. It's just an example that I kind of randomly picked so I could just randomly find an article in the literature and see how it worked. Now, CVD is a way of depositing material on a silicon wafer. It's done in a furnace. You heat it up. You introduce some gases, a chemical reaction occurs on the surface of the wafer, and in this case, tungsten metal is going to be deposited. The deposition rate has a model that has regions of diffusion controlled and reaction controlled in terms of its temperature. And the goal in this particular paper is to measure the activation energy in the diffusion-controlled regime. So over here in this regime, a typical Arrhenius plot where I plot the log of the deposition rate versus 1 over the temperature. This is a straight line in the reaction-controlled regime, and the straight line has a slope of the activation energy divided by Boltzmann's constant, or the universal gas constant in other units. So all we're really trying to do is fit a straight line, this curve, and extract the slope. And here's the data. Now, again, I kind of randomly selected this paper. I don't know really anything about these authors of this paper. I don't mean to criticize anything that they do. I'm just showing you kind of typically how people in the scientific world present information, and how it's very frequent that they don't present all the information that a reader actually needs to fully understand and appreciate the information and the analysis of this data. So if you were to read this paper, not just this graph, but the description of this graph as it's presented in the paper, you can ask yourself, are all of the aspects of data being properly presented and communicated in this work? And again, our goal would be to grab the slope of these curves, and that provides us the activation energy of this chemical reaction. Now, recall from Lecture 2 that data has lots of pieces to it, beginning with the definition of the thing being measured and ending with the measurement model that's used to extract this data from the specific measurements that are being used. Now, often this first and last point are and can be somewhat ignored in the presentation of data. That's because sometimes the definition of the thing being measured is pretty obvious or well known and doesn't really need to be discussed. In our case, we're looking at deposition rate, and the deposition rate, angstroms per minute here, is the rate at which the thickness is being increased over time as the material is being deposited. It's very easy to understand. We don't need to talk much about that definition. There's some details actually that matter in terms of how we extract uncertainty estimates for that measurement that we'll get into. But often the first and last point can be ignored. Sometimes, though, they need to be discussed. The middle four things, though, are the measurement value. Everybody provides that. But then the estimate of the uncertainty of each measurement, experimental context, and the uncertainty of that context are all essential items that frequently are ignored when data is presented. And if you were to read this paper carefully, look at the graph, look at how the data is described in the paper, you'll find that there is no mention of measurement error. So we have these data points for deposition rate at a particular temperature and other process conditions, and there's no error bars shown. There's no mention of an estimate of the uncertainty in that measurement. And no discussion of how you might even go about obtaining that uncertainty estimate. So that is a missing piece, an important piece of the data. Now it does mention the temperature value, right? The x-axis has an uncertainty of plus or minus 2 degrees, and that's an important thing to know, and it is mentioned in the paper, not the measurement of the deposition rate itself. It very carefully discusses the context of the experiment. That's very, very well described. But there's no mention of context uncertainty. For example, we see that the deposition rate is a function of pressure, and it's a function of gas flow rates. And those values are provided, but no discussion of what the uncertainty, 2 torr plus or minus what? We don't know. And finally, they extract the slope of these lines. They assume all these lines are parallel, and an assumption that's made. I don't think they actually verify that assumption. They assume all the lines are parallel so that there's one activation energy that's independent of gas flow rate and pressure. And they give you a value, 0.71 electron volts per atom, as the activation energy. Well, what's the uncertainty in that value? It's extremely important when you present the result of your analysis, in this case the slope of that line, that you present not only the best fit slope, but an estimate of the uncertainty of that slope. Is it 0.71 plus or minus 0.01, 0.1, or 1 eV? If you don't know what that uncertainty is, then you don't know how to interpret that value that's provided. Now we can kind of look at the graph and eyeball a fit and say, those fits aren't too bad, so, maybe the uncertainty is not great. That's about all you can say unless we do a more thorough statistical analysis. Well, if you don't know how to do a linear regression, a best fit, to get a slope and extract this 0.71 value with an estimate of the uncertainty, well, that's something you're going to learn in this class. First, to mention about how they measure the deposition rate. I said last time, with respect to the measurement model, that it's very infrequent we measure directly the thing that we want. Instead, we make an indirect measurement. In this case, the thing that's being measured is the thickness of the tungsten. Those thickness values are then plotted versus deposition time, and they're fitting a straight line to those deposition values after some initial thickness is deposited. So we have an initial mechanism of depositing material that's much faster, and then it slows down to this H2 dissociation limited deposition rate. And then the slopes of these curves are assumed to be the deposition rate. So we do a best fit, probably a ordinary least squares regression, although it's not mentioned in the paper exactly how they did it. They extract a slope. They say that's the deposition rate. What's the uncertainty in these slope values? Well, that becomes the uncertainty in the deposition rate that's used in the next analysis. There's also a series of assumptions that are being made here, none of which are described in the paper, but you can sort of figure out what they are. We're assuming that the deposition rate is a constant over time. It doesn't change with the thickness of the tungsten. It doesn't change with deposition time. It's a single value for the deposition rate, and therefore a straight line model is appropriate. Is there any way to check that assumption? The authors don't do it. It would be nice if they had done that, but the only thing we can do is probably just look at this graph and say, yeah, looks pretty good, like it might be linear, but is there a better way to test that assumption? How appropriate is a model given a certain set of data? That will again be a topic that we use in this class. So I just randomly picked a paper. In fact, this is the first paper I looked at when I was just trying to find an example to use in this class. And it provided very, very typical kinds of ways in which data is presented in the literature, where some important aspects of the data are properly presented, but others are not. And it's actually kind of rare to find a scientific publication that does everything just right. Well, my hope is that after you've this class, that if you ever have to write up an experiment, present data at a conference, in a publication or a technical report within your company, you'll be able to present that data with all of its detail so that there's no uncertainties, pardon the pun, involved in what you know and what you present to the reader. So what have we learned in Lecture 3? Well, as a review, you should be able to tell me the 6 parts of the concept data, and then which 2 parts can sometimes be taken for granted, so that you really need to focus on the middle 4. Not always, though. You have to be a little bit careful there. And then finally, this is just for you to think about, how often do you see data presented where all of these parts are carefully documented? And maybe you can get yourself into the habit of, whenever you look at data being presented in a technical publication, get in the habit of asking yourself, well, what's missing? What have they failed to tell me that they should have told me? It's good practice to do that, so that you're in the position of presenting, communicating data to others. You can do it right. You can put all of the information that's needed there. Well, that's Lecture 3. Thank you for listening.